Look right here at this massive crossing. This crumbling steel structure is one of the most terrifyingly deficient, heavily trafficked bridges in the whole of America, scoring a horrific sufficiency rating of only 6.6 out of 100. Every single day, nearly 90,000 vehicles are forced to squeeze onto a narrow deck with only 4 active lanes and absolutely no safety shoulders. That is exactly why the state is moving forward with the massive $2.4 billion Calcasieu River Bridge replacement project to tear down this dangerous bottleneck. This massive corridor project in Louisiana will stretch across 9 kilometers of highway. Will engineers be able to pull off this mega project before the ticking time bomb fails completely? And how did we even end up with such a massive disaster waiting to happen? To find that out, we have to look back to 1952. That was the year this massive bridge opened to traffic as a primary part of the United States Highway 90 system. Back then, it was not part of an interstate at all. It was actually called the Louisiana Memorial World War II Bridge. They built this steel truss bridge towering 41 meters above the waterline. That massive height allowed deep cargo vessels to navigate upstream to local chemical plants and oil refineries without stopping traffic. Before that, drivers were stuck waiting hundreds of times a month for an old drawbridge to open. Engineers designed the bridge to last 50 years and to handle 37,000 vehicles every day. It was a local landmark, famous for having over 5,000 cast-iron crossed pistols built right into the railings. But over the decades, the bridge was absorbed into Interstate 10 and traffic exploded way past what anyone expected. Now, it is a relic from a different era, trying to survive in a world it was never built for. You might be wondering why we cannot just repair this old bridge instead of spending billions on a brand new one. To understand that, we need to look at the massive technical problems that make this bridge a daily nightmare. For starters, the roadway provides only 4 active lanes on a deck that measures a narrow total width of roughly 16 meters. This complete lack of shoulder space means that any stalled truck or minor fender bender instantly shuts down traffic across the entire structure. There is nowhere for a disabled car to go. That is terrifying when you are stuck on a bridge that high. And speaking of being high up, the physical shape of the bridge creates another massive problem for modern traffic. The bridge is notoriously steep, featuring a grade of up to 5% on the western approach. When heavily loaded commercial trucks hit that slope, they slow down drastically. Sometimes their speed drops to just 32 kilometers per hour. This massive drop in speed creates huge differences between slow trucks and faster passenger vehicles. This heavy friction leads to constant multi-vehicle collisions. In fact, a crash in 1981 involved 26 vehicles and killed 3 people when a truck ruptured its fuel tank on an expansion joint. The continuous heavy traffic has taken a massive physical toll on the bridge itself. The structure currently rates a 3 out of 9 in overall structural evaluation. That rating means it meets only the bare minimum standards required to remain open without falling apart. The continuous shaking and heavy vibration caused by vehicles have caused constant electrical and mechanical failures. For example, streetlights on the bridge fail repeatedly because the aggressive shaking breaks the lights. This leaves the massive span without reliable lighting at night, making it even more dangerous. Maintenance teams completed minor emergency repairs in 2012, replacing 48 girder pins and resizing connection plates. But studies confirmed that total failure remains a long-term possibility without a complete replacement. This brings us to the next big question. How do you replace a massive highway bridge without shutting down one of the most important freight corridors in the nation? You cannot just blow it up and start over. That is where the engineering for the new corridor comes into play. The new bridge will be built slightly north of the old steel truss structure. The replacement project stretches across a corridor of about 9 kilometers, completely rebuilding traffic approaches and interchanges. The primary engineering goal of the replacement project is to solve the massive capacity and safety flaws of the old infrastructure. To achieve this, engineers designed a structure that provides 6 standard travel lanes and 2 auxiliary lanes. This will successfully double the capacity of the corridor. Each lane and continuous shoulder on the new bridge will measure 3.66 meters in width. This will finally grant ample clearance for traffic and disabled vehicles. Another massive design change is the reduction in the physical height of the bridge. The old bridge reaches a grade elevation of more than 46 meters at its crest. The new structure will feature a heavily reduced height between 22.8 and 28.9 meters. This lower elevation translates to a vertical grade of roughly 3%. This flatter path will prevent the aggressive speed drops of heavy commercial trucks that caused daily gridlock on the old bridge. But building a brand new mega bridge in this area brings up a terrifying environmental challenge. In 1994, a pipeline transfer failure occurred at a refinery located on the river. This failure released between 8,600,000 and 21 million kilograms of ethylene dichloride into the ground. Ethylene dichloride is a heavy, toxic chemical compound that easily settles and moves into the groundwater table. Environmental sampling revealed that a toxic plume had spread beneath the surface. This plume migrated directly into the right-of-way required for the reconstruction of the new bridge and its western approaches. This plume presented severe hurdles for geotechnical and structural engineers. The ground in this area of the country is characterized by alternating layers of soft deposits, silts, and tight clay. This geology naturally traps heavy toxins above a deep drinking water aquifer that supplies water to thousands of local residents. Engineers voiced strong concerns that standard deep foundation pile driving or boring could puncture the protective clay layers. If a drill or a pile punctures that clay, it would create a direct vertical hole. This would allow the toxic chemicals to travel straight down into the drinking water supply. Because of this danger, engineers had to think of a way to model foundations that would not go too deep, but would still hold up the massive bridge. They have been studying ways to optimize the piles and calculate their long-term strength. In soft clays, the ultimate bearing capacity of a driven pile grows heavily over time as the soil remolds around the shaft. This effect is heavily evaluated using standard rate-based models to ensure long-term stability without requiring excessive driving depths. Structurally, the main spans of the new bridge will rely primarily on pre-cast, pre-stressed concrete girders equipped with cast-in-place composite concrete decks. Engineers selected these specific elements because they provide high structural durability, fast assembly, and resistance to localized fatigue. To preserve the history of the previous bridge, architectural plans incorporate decorative towers that hold replicas of the original crossed pistils. Furthermore, modern lighting will be arranged in an arch shape on the bridge to mimic the silhouette of the old steel trusses. A separate critical component of the corridor engineering involves shifting local road elevations to remove intersections with railroad tracks. The project will construct an elevated overpass at Sampson Street. This overpass will allow vehicles to bypass heavy trains that previously caused daily traffic blockages in the city of Westlake. Pre-construction activities and investigations advanced heavily after the project reached its financial close in late 2024. Teams completed mapping rights-of-way, obtained permits from the Army Corps of Engineers and the Coast Guard, and finished initial test piling operations. Major construction across the corridor is scheduled to start in the spring of 2026. Construction teams will execute work across 4 distinct segments simultaneously to accelerate the timeline. To maintain continuous commerce during project delivery, the interstate will remain open to traffic across the old bridge until the new structure is complete. Engineers have already executed trial embankment operations north and south of the old bridge. This is where teams test how the ground settles with the significant amount of weight of the dirt. Furthermore, existing utilities that were previously scattered across the alignment are being consolidated into a centralized duct bank. This clears the path for foundation work and improves future maintenance access. Traffic is anticipated to officially shift from the legacy bridge onto the new bridge in February of 2030. Once that shift is complete, mechanical demolition of the legacy steel truss bridge will commence. The removal of the 1952 bridge is expected to be complete by November of 2031. To try and solve the massive problem of the toxic chemical plume, scientists and engineers tested several advanced techniques directly in the contaminated soil. One method they looked at was electrical resistance heating. This process passes electric currents through the soil to boil the moisture and recover the toxic chemicals as vapor. However, massive hurricanes caused significant downtime and lost temperatures, and the boiling process caused unacceptable soil settling that would make bridge foundations unsafe. Another technique they tried was in situ chemical oxidation, where oxidants are injected into the ground to destroy chemical bonds. But this proved incredibly difficult because the oxidants would not diffuse evenly through the tight clay layers. They even tried enhanced bioremediation by injecting specialized bacteria and nutrient slurries to break down the toxins. This was highly successful in reducing toxicity levels without making the ground settle, but it still could not clear the area completely. Engineers even tested a massive auger that was 3.66 meters in diameter. This massive drill blended the soil while injecting steam and hot, compressed air. This massive system reduced chemical concentrations by up to 98%, but it failed to fully clean the groundwater. Since none of these remediation techniques could yield a perfect subsurface clearance, structural engineers had to carefully adjust the project design. The project baseline schedule accounts for continuous environmental monitoring during the boring and test piling operations to ensure nothing breaches the clay barrier. Please subscribe to the Building Impossible channel and turn notifications on so you do not miss any of our videos exploring massive engineering marvels.